Hello, hi, welcome to this video presentation of my SIGIR 2021 publication. This is a different video than the one that's available at the conference. I've recorded this especially for YouTube, so that's available to the wide public. The paper is titled Computationally Efficient Optimization of Plackett-Luce Ranking Models for Relevance and Fairness. It's an open access paper, so you can find the PDF in the description. You can also find these slides in the description and a link to the code that we used for this paper as well. All right, in this paper, the goal was to find a method for optimizing Plackett-Luce models for relevance and fairness ranking metrics. So to optimize these models with respect to metrics that are either about relevance or fairness of rankings. I wanted an unbiased method. So I didn't want to rely on heuristics or on bounding, but to find something that an expectation will give you the real gradient so that you can do stochastic gradient descent in an unbiased way. Also, it needed to be a computationally efficient way of doing things. With ranking problems, you can very easily get into these large combinatorial problems that you can never do the computation of because they're so incredibly complex. So we want to stay in the feasible realm of computation. Our contribution is a novel algorithm, Plackett-Luce rank, which is a novel sampling-based method that can very quickly estimate Plackett-Luce gradients in an unbiased way. Now, the paper is mainly a long derivation that proves that this estimation is unbiased. I'm not going to repeat that here because, well, it would be a very long and boring video, right, if we go through this mathematical derivation. Instead, my aim is to keep this video shorter, but hopefully more interesting by just talking about the main findings and not all of the steps in the derivation. Of course, if you're interested in derivation, you can find the paper in the description. Right, so I want to start with the motivation. Why did we choose to optimize a stochastic probabilistic model and not a deterministic model? After all, deterministic models are the way that we used to do ranking, and it's still the way that you see ranking in many places. That traditional way is you have a model M, and we're going to use the scores that this model gives to each item, so each item D in our collection, which is capital D, and we wished it to give these scores in order of relevance so that if we sort according to the scores, the ranking follows relevance as well. In other words, if we have one item that's more relevant than another item, we want the score for that item, according to the model, to be greater than the score for the other item. Now, usually this is applied in a deterministic model where you're just going to follow the scores, and that's the ordering of items that you're going to show to the user. However, in recent years, we've seen arguments being made for probabilistic ranking models instead of this deterministic approach. The first and I think most important reason is due to fairness. A problem with a deterministic ranking is it's going to give most attention to a single item because there can only be one top one item, number one item, and that's going to receive the most attention from users. Most users are going to look at that item. This can be very unfair if there are other items that are equally relevant or equally preferred by the user, or almost equally preferred. Even though the difference is very small, the difference in attention can be very big in this case. And if they're exactly equally relevant, then there's one item that's going to be number one. It's going to be getting a lot more exposure or attention from the users than all the other items. This is unfair. You can imagine, especially in situations, for instance, if you're selling in e-commerce, if you're selling items from different vendors, this may give one vendor an arbitrary, unfair advantage. If you're thinking about ranking things like job applicants, as happens on some platforms, this could really be the difference between one person getting a job and another person getting a job, even if they're equally qualified. The point here is, if you use a stochastic ranking model, which is a distribution over multiple rankings, you can actually give multiple items the chance of being in a rank. So there can be multiple items that have a chance of being the top one item. And in this way, you can actually fairly distribute the exposure over items. You can make sure that the amount of exposure that they get is in proportion to how relevant they are. That's a very important argument for using a probabilistic ranking model instead of a deterministic ranking model. Another one is exploration. If you're learning from user behavior, like user clicks, a stochastic ranking model can try different rankings according to its uncertainty. So instead of saying, okay, I'm going to show this ranking because I think it's the best, it can say, well, I have this ranking and I have these other rankings, and I'm not entirely sure which one is the best. By showing them with different probabilities, you can actually learn from that and learn which one is the best model. So it's already been used for fairness and exposure. There are more reasons why probabilistic ranking models may be preferred, but I think these situations or these arguments really make a strong case already. The other part of this paper is ranking metrics. So we want to optimize ranking metrics. And what I mean with ranking metrics is what I want to display here. So explain here. So for any ranking y, a ranking metric, which can be very arbitrary, has to use, but we call it a ranking metric if it uses a weights per rank. So we have the theta k here. So for rank k, we have this weight, which is just a number. And we have the relevance of items. So we have a number for each rank, and we have a number for each item. And then we have the probability by the policy pi of showing this ranking given a query Q. And then the metric value, the reward you might say, for a query is just a summation over all of the rankings that the policy may show according to the probability of that this ranking is shown. So this is just an expectation over rankings. And then for each rank in the ranking, the weight per rank multiplied by the relevance of an item. So I'm going to use the shorter notation for the rest of this presentation, which uses rho for the relevance. So what we really here have is an expectation over rankings. And for each ranking, we're going to go over each rank, how likely, so sample according to how likely that ranking is to be displayed. For each rank, you have the weight, theta, multiplied by the relevance of the documents that's there, and then you sum over all the ranks like that. If there are multiple queries, we just take an expectation over query distribution, so more frequent queries have a more heavy weight than less frequent queries. This description can be applied to many well-known ranking metrics. So precision, recall, discounted cumulative gain, DCG, average relevant position, ARP are examples that are very well known. They fit within this description, so our method can optimize all of them. All right, that sets the stage. Now let's take a look at some background. I want to focus on Plackett-Luce models, because these are the models that we want to optimize. So let's first describe what they are. Plackett-Luce models are very old. As you can see from my citation here, they're about half a century old, and they're a way to model how someone may make a decision choosing one item out of a collection of items. The way it does that is by assuming that it's determined by the value of the item that you may choose in comparison with the sum of the value of all the items. So the probability of choosing item D out of a collection, capital D, is the value of this item, which should be some positive value, could potentially be 0, but usually it's positive, so there should be some value, divided by the sum of all the other items, the value of all the other items, so the total value. So this is really just the percentage of value that this item makes out of the total amount of value that there is in the collection. And you've probably seen this model before if you did anything with deep learning, because the softmax function is basically an instance of a Plackett-Luce model, where we use the exponential function to ensure that we have positive non-zero values. So in a softmax function, we take e to the power of the output of our model score, and this is going to be the value that we assign to the item, or that the model assigns to the item, divided by the sum of the total value of all the other items. So the sum over each item. you probably recognize this as a softmax function if you've done anything with classification in deep learning, but you can also see it as a Plackett-Luce model. Now, this isn't a ranking model yet. To make it a ranking model, we have to apply it repeatedly. So we're going to repeatedly apply this softmax model, this Plackett-Luce model, to the unplaced items. So we're first choosing one item, then we're seeing what's left, and from that we're choosing the second item, and so forth and so forth. The formula we get is the following. So the probability of policy pi choosing document D given the ranking up to k, so the items that have been placed so far, which are k items, and the collection of items, is, well, here we have the value of the item according to the model, but we multiply it with an indicator function that indicates whether this item has not been placed already. Because if the item has already been placed, we don't want items to be placed multiple times in a ranking, because then it's not really a ranking anymore. So we want to give them a 0 value, so they have a 0 probability if they're already placed, and this is what the indicator function does. So this becomes the item value or the item score if the item hasn't been placed already. And then down here we have the sum of all the unplaced item scores. So it's just a sum over all the items where we remove the ranking so far. So this is just a softmax function applied to all the items that have not been placed so far, where y indicates what's been placed, up to k indicates what's been placed up to this point. The probability of the complete ranking is just the product of each of these placements. So the probability of item placement 1 times that of item placement 2, and so forth. Now, this is a valid distribution. This gives us a real distribution over many possible rankings. But something that you might foresee here is that could be expensive to compute all of these probabilities. Luckily for us, we can actually sample from this distribution without having to calculate any of the exact probabilities. And you can do that by what's called the Gumbel noise trick. If you sample noise from the Gumbel distribution and you add it to the scores that the model gives, and then sort according to those new values, you have a ranking that follows the same distribution. So you can sample from this very quickly without having to compute any of the actual probabilities. I highly advise you to look into this trick if you're going to apply this model in practice. Then, how do we optimize this Plackett-Luce model now that we know what it is, or Plackett-Luce ranking model, I should say? The prevalent existing approach is to use policy gradients. And policy gradients use the very well-known log trick from the reinforce algorithm, which is a reinforcement learning algorithm, which uses the following basic equation, which is the gradient with respect to a value is that value multiplied by the log of that value. This has to be a positive value, of course. And you can apply it to probabilities. And the reason this is interesting is because now you can turn this into an expectation. You can now sample from pi and then use the log probabilities instead. This is exactly what's been done to get what we call a policy gradient. We sample n times, so we want to update our model pi, and we're going to compute the gradient of pi by first sampling n samples. So we sample n rankings from our current model, our current policy, and then we can unbiasedly estimate the gradient. So the gradient with respect to the reward is going to be an average, or estimated by an average over all the samples, where we first take the gradient with respect to the log probability of the complete ranking. So the probability of getting the entire ranking multiplied by the observed reward. So the reward the metric that this ranking would give us. So we just, again, we sum over all the ranks, and then we have these rank weights multiplied by the document weights for each position. So we sample n rankings, and then we take the gradient is the log gradient of each ranking weighted by the reward that we get for that ranking. So the more reward a ranking gets, the more weight it has in this gradient. This is quite straightforward. However, it's also not specific to ranking or Plackett-Luce models, and it can be quite computationally expensive. So the goal of this paper was to see, can we find something that's more sample efficient, that needs less samples to get an accurate estimate, more computationally efficient, so something that we can compute much faster, and is that possible if we take into account the specific properties of Plackett-Luce ranking models? Turns out it is, and that's where we get to the method section. So before I introduce the Plackett-Luce rank algorithm, we have one step in between, which we call the placement policy gradient. And this comes from the observation that a reward before a rank k should not influence the probabilities of a rank of after k. So to illustrate this, imagine that you have a high reward for document 1. The first document that's being placed gets a very high reward. Should that reward affect the probabilities of the documents that you're going to place afterwards? Well, it shouldn't, because whatever is the second document you're going to place, it's going to have no effect on that reward that you got for the first document. So they're kind of independent. It doesn't matter what the second document is. The reward for the first document, you already have it. We can prove this by rewriting the metric so that you can actually see this in the formula. So we rewrite it so that we first sum over all the ranks. We have the rank weight multiplied by all the possible partial rankings. So all possible rankings of size small k. So for instance, if k is 3, all the possible top 3s basically. The probability of each of those partial rankings multiplied by the relevance that this partial ranking, the item at rank k in this partial ranking has. What you see here is that the relevance never interacts with any probability after rank k, which was our intuition. But now we have an algebraic proof, and we can use this to get a new estimator, which again uses n samples from the policy. Again, it is going to average over those samples, but now it's going to sum over each rank. Then it takes the log probability of the item placement at rank k. So the item that we see at rank k, what's the probability there? We're going to take the gradient with respect to the log probability, and we'll multiply it with the reward received at rank k and after. So we place this document. What was the reward that we observed after placing this document? That's what we're going to weight the gradient by. And this is already more sample efficient than the previous policy gradient. Our experiments show this is much better. The only property that we used here is that we know the metric. We know that this is a ranking metric, so we know that later documents can't affect the reward at earlier ranks. We're not using any properties of the Plackett-Luce model itself. That's why this is not called Plackett-Luce ranking yet. But the next method, which takes this as a starting point and then further derives something new, does do that, which is why we call it Plackett-Luce rank 1. You can probably already tell that there's going to be Plackett-Luce rank 2. But we'll start with 1. We further derive, we take this placement policy gradient, and in the paper we further derive another estimator that makes use of the fact that pi is a Plackett-Luce ranking model. And what we get is the following. We get the gradient of the metric can be estimated by a sum over each item in the collection, where we take the gradient with respect to the score. So this is basically backpropagating into the model. So if this is a neural network, this is where the backpropagation into the network starts. We're multiplying this gradient by something that's an average over all of our samples. The first thing is the reward following the placement. So we look at the reward at the rank where this document was placed in the sampled ranking. And then what's the reward that we receive at that rank and afterwards. So this is sort of the the reward that you might say followed the placement of this item. If the item was not placed in the top k at all, this is going to be 0, of course. But this value tells us sort of how good that placement was. Because if we received a very high reward, then we should probably place this document there again. However, that's not all. There's also the risk. This is the second factor here, what I call the risk imposed by the placement probability. So we're going to sum over all of the ranks before the placement, but also the placement itself. And we take the probability that the item was placed here. So if we look at the ranks earlier, this is the probability that this document or this item was placed before, instead of the item that was actually placed. So it's sort of like how likely was this item to get in this position instead of the item that's actually there. And it's multiplied by the reward after this rank. That's why I call it the risk. It's kind of how likely is this item to intervene here to make sure a different ranking happens at this point, times how good was this ranking that it would have presented. So it's kind of a risk. It's a risk imposed by the placement. I want to emphasize what I'm doing here is I'm putting my own intuition on a method that we derived mathematically. It's not that I sat down and thought, you know, the gradient should be first the reward and then minus something called the risk. No, we started with the formula of the metric at the start, and we derived this. So it's not something that I designed, more something that was discovered from derivation, and I'm now giving you an intuitive explanation of what's happening here. An important property is that if you have n samples, you can compute this gradient in a complexity of n times k times d, which is very doable. We don't have anything exploding here, nothing exponential. Right. So far, so good. There is something strange here. There's a sort of a flaw, which is we can see that if there's items in that are in your n samples are not in the top k of any of the rankings. So we have n sample rankings. If your an item is not in any of the top k of those rankings, it's always going to get a negative gradient with respect to its score. Why? Well, this is going to be 0 if it's not in the top k of any of the samples. Then this sum is going to be nothing, right? It's going to, the rank is already greater than k, so nothing happens here. But this is definitely going to be a negative value because it will have a positive probability, and if there's any reward received, then it's going to turn into a negative gradient. So you can always expect a negative gradient for these items, even if the items have a high relevance, right? If for some reason the items have a low probability of being in the top k, but actually have a high relevance, they're still going to have a negative gradient and be pushed away from the top k. That seems counterintuitive. It doesn't seem like something that we want. If n is large enough, this is not going to be a problem, but if n is smaller, this may really drive the model in the wrong direction. So to solve that, I found a solution. And the nice thing is this solution actually maintains the computational complexity. So we don't need more computation, but we can still avoid this flaw. It's the same setup. We still sum over all of the items, the gradient with respect to each item score. We still have the average over all the samples, but now we look at the reward after the placement, so not including the direct reward. So we look at rank +1. So not what happened when we placed this item, but what happened one rank later. And instead of the risk, we have something else here now, which is the expected direct reward minus the risk of placement. Again, we sum over all the ranks, where we go all the way from the first rank up to the rank and including the rank where it was placed. We have the probability of placement, and then we have the reward that you receive directly. So the reward that you receive if you were to place the document there instead of the document that's actually, the item that's actually there, minus the following reward. So that gives us the risk. And this can actually give you a positive weight. If you have a very high relevance, this part here can weigh up to that part over there. So this allows items that are not part of any of the top k's of any of the sample rankings still to have a positive weight. And we'll see that this increases the sample efficiency. Great, so these are the new algorithms. But you may remember I started this talk by motivating the need for this algorithm for instance, a fairness-based metric. And this far I've only talked about relevance. So that's what we'll do now. We'll look at fairness in exposure, particularly at rank-based exposure. What is rank-based exposure? Well, exposure is another word of saying how many people are going to see your item, right? How many people are going to see this item in this rank, in this ranking. And the assumption is usually that it's only determined by the rank at which you place an item. So if you know where the item is in the ranking, you roughly know how many people are going to look at it. So you can write it out in this formula where we have the expectation, the exposure for item D under query Q. And it's an expectation again over rankings according to the policy. And then we just want the weight for the rank where the item is. So we can do that by summing over all ranks and then using an indicator function to indicate which is the document that we care about. And that gives us the theta weight for that rank, where theta now indicates the attention that you get from users. An interesting observation here, an important observation, is that this looks a lot like the relevance metric that we saw earlier. We're going to use that property in a minute. First, I want to talk about the fairness metric that we use in the paper, which is a pairwise disparity-based metric, which means that we're summing over pairs of items, and then we're looking at the disparity between those items. So sort of how fair, how unfair or fair is this item being treated with respect to how this other item is being treated. And what we want is the exposure of the items to be in proportion to the merit or the relevance of the items. Existing metrics take the exposure and divide it by the relevance. There's a big problem that arises there, which is if the relevance becomes very small, or even zero, your metric is going to explode, right? That value is going to explode. If it's exactly zero, then it's undefined. That gives a lot of trouble because in many collections there are many items which are not relevant at all for certain queries. So I thought that an alternative was necessary, and this is what I propose, which is you take the exposure of one item, the first item, and you multiply it with the relevance or the merit of the second item, minus the exposure of the second item times the relevance or merit of the first item, and that difference you square it so that it actually becomes something that you can optimize, or always a positive value. And this will force the ratio between the exposure and the merit or relevance of an item to be the same for both of these without having to divide by any relevance. So this also enforces fairness, but it doesn't have this problem of exploding. So, we needed this because I'm using data sets that have zero relevance objects in them. And the algorithm is not limited to this metric. So you can apply it to any rank-based exposure metric as long as you can do the following. The gradient of the metric with respect to the model is a summation over all of the documents in the collection, where you first take the gradient of the metric with respect to the exposure. This is going to tell you how much more or less exposure should this item get according to this metric. So is this an item that is underexposed or overexposed with respect to fairness? So it tells us whether this should be decreased or increased, multiplied by the gradient of the exposure with respect to the model. So how should the model change for the exposure to increase? So you multiply these things, that gives you the gradient with respect to the score, and then sum over all the documents, and that should get you the gradient. I think most fairness metrics you can do this with. If you can apply this trick, you can use Plackett-Luce rank as well. Right, so this is what that turns into. Again, the paper shows you all the details. But the main trick is the exposure formula, the exposure function, is really similar to the reward function we saw earlier, except we have an indicator function here instead of a relevance-based function. If we apply that, if we combine that observation with the previous formula that I showed you, where we sum over all the documents, you get the following. So because it's so similar to the relevance metric, we know that Plackett-Luce rank can be applied to this by just replacing the relevance with the indicators functions. And after we sum all of these metrics for each of these documents, we end up with a single gradient, which is the following. So now we have the fairness-based metric, where we're taking the gradient with respect to. Again, we take the gradient with respect to each model score, but now instead of the direct reward, we have, or the reward after placement, we have the exposure weight for each rank multiplied by the partial gradient of the metric with respect to the exposure of the item that's placed there. What does this mean? Well, we're going to place this item yk, so the item at position k in this ranking, and we have the one number, which is how much the fairness metric thinks the exposure should be improved to this metric, and then we have the exposure that it gets to this rank. And both of these, if both of these are high, then we improve the probability of the score. So in the probability of us doing this again. So if placing a document leads to a combination of documents that, according to the metric, the fairness metric, should receive more exposure, receiving a lot of exposure, then we're going to improve the probability here. On the other hand, we also have the second factor, which looks at the direct consequence, like how much exposure will this item get from placing it at each position, times how much should it get more according to our metric, the partial gradient, I mean, minus the risk. So how much is the item getting in the way of other items getting exposure that should really get exposure? Again, this is not something that I designed. I didn't, thought, hey, this is a good idea. Instead, it's something derived, where I'm now giving you an intuitive explanation of how it appears to work. Nonetheless, I think this is extremely cool, right? We have one ranking algorithm that works for both relevance and fairness. As far as I know, this is the first time that we can apply the same method to both of these problems, outside of just normal policy gradients, of course. All right. Of course, we did some experimental results. So we looked at how much time do you need to reach a certain amount of performance. The performance metric here is DCG. Again, that fits in the ranking description I've shown you so far. And the x-axis here is the minutes trained. So how long did it take to train? So for how long have we been training it? What's the performance? This is the average of a high number of runs. I don't remember how many runs, but enough for statistical significance. We have the policy gradient method over here. As you can see, it doesn't do very well. The problem is that it's taking a lot of time to compute. We're using the TensorFlow framework to do that. And it needs a lot of samples to converge at high performance, which it's not getting in this setting. We're giving all the methods the same amount of samples, but it's not enough for policy gradient. The lambda loss is also something that we looked at, a very famous baseline, of course. It's much faster, but it doesn't converge at optimal performance because it actually bounds the metric instead of optimizing it. So instead of estimating the gradient directly, it gives us a gradient that on a value that bounds the metric and not the actual metric. It appears that it makes it converge at a suboptimal place. Then we have the placement policy gradient. We see it's much better than the baselines. This is mainly due to the sample efficiency. So it actually, with the same number of samples, it can get much higher performance than the policy gradient. Then Plackett-Luce rank 1 has the same sample efficiency, but you can compute it faster, which gives you another boost here, another speed up. And then Plackett-Luce 2, which compared to Plackett-Luce rank 1 is computationally more expensive. It takes more time to do the estimation. but its sample efficiency is so much better that you still get an improvement in performance, which is great. Clearly, Plackett-Luce rank 2 is the best option here, right? It reaches the highest performance and it reaches much quicker than any of the other methods does. And if you look at the difference in minutes, it can really save you a lot of time here, choosing Plackett-Luce 2 over, for instance, the placement policy gradient. Here are the results on the other two data sets. The conclusions stay roughly the same. The difference between Plackett-Luce rank 2 and 1 is smaller on the MSLR data set, but apart from that, there's nothing very different. We still have the same conclusion. There's still much better choices than the baselines. Of course, we also did an experiment with fairness. So on the Yahoo WebScope dataset, we minimized the disparity metric that I've shown you before. And the difference between the new methods is not so big, but they're still much better choice than the baselines. All right, to wrap up the talk, I've introduced a novel algorithm, Plackett-Luce rank, which is a learning to rank method specifically for Plackett-Luce models. It's a sample-based gradient estimation method, so we're estimating the gradient based on samples from our current model. It's unbiased. It gives us, in expectation, the actual gradient. So it's not a heuristic. It's not using any bounds or anything like that. It's computationally efficient. We're avoiding any combinatorial problems. It's applicable to both ranking metrics about relevance or fairness, which is very nice. It's the first time that we have a method for both of these at the same time. It also shows that these problems aren't that different. If you want to continue on our work, the code is available. The link is also in the description, as is the PDF and the slides. And finally, I want to say something about future work. So unfortunately, there was an important work that we missed while making this paper, which is the stochastic rank algorithm. So this was published at ICML 2020. They optimize deterministic ranking models, but they use noise to stochastically smooth a ranking function. So they also apply sort of a stochastic approach, but they're not optimizing Plackett-Luce models. This algorithm has very strong theoretical properties. If you check out the paper, it's mainly a proof about many of the properties of this algorithm. And we think that it could also be applied to Plackett-Luce models with some adaptations with comparable computational complexity. What's very promising here is that we now see multiple methods being developed independently that are both computationally efficient, effective, broadly applicable to learning to rank, and have a stochastic sampling-based approach that gives you unbiased gradients. It could be that in a couple of years this becomes the main way of doing learning to rank, which would be very interesting. Then that leaves me with nothing more than the references. And I want to thank you for watching. I hope to see you again for a future video. Thank you very much. Bye-bye.